Welcome back to the deep dive. You hear quantum internet, and, well, it sounds like something straight out of science fiction, right? Like years away.
Definitely feels that way sometimes.
But what if I told you a really significant step towards making it real just actually happen?
Yeah, that's exactly what we're getting into today. There's this groundbreaking silicon breakthrough from researchers up at the University of British Columbia, UBC.
Right.
And our mission, sort of, for this deep dive is to unpack that development, look at the huge challenges it tackles, and, figure out what it means for our connected future.
Right. And think of this conversation as your shortcut to really understanding this complex but super important advance. We'll pull out the key ideas, maybe some surprising bits, to help you grasp why this is such a quantum leap, excuse the pun.
Hey, yeah.
So let's dig in. Where do we start? The problem itself.
Yeah, I think we have to start with the basic communication problem in quantum networking. It's fundamental. So quantum computers, right? They actually process information using microwave signals.
Okay, microwaves, like short range.
Exactly. Think very specialized radio waves, great for the internal stuff. But, and here's the kicker, to send that quantum information over long distances, city to city, across continents, it absolutely has to be converted into optical signals. The kind of light signals that zip through the fiber optic cables we already use for the regular internet.
And that conversion, that's the tricky part, I'm guessing. These optical signals must be incredibly delicate.
Oh, extraordinarily delicate. We're talking about a level of fragility where, even the smallest disturbance, the tiniest bit of noise during that microwave to optical conversion can just completely obliterate the quantum information.
Wow. So you lose the signal and you lose the quantum magic, like entanglement.
Precisely. You lose quantum entanglement.
Yeah.
And entanglement is, it's the key phenomenon that quantum computation relies on. It's that really weird connection.
The spooky action at a distance thing.
That's the one Einstein famously called it. It means two particles stay linked, perfectly correlated no matter how far apart they are. If you lose that entanglement during the signal conversion,
and then the whole quantum advantage is gone.
Poof, gone. The very reason you're using quantum communication in the first place disappears. And that has been a massive, massive roadblock for building a real quantum network.
Okay, so given how fragile this sounds, this need to convert signals without losing entanglement.
Yeah.
What did the UBC team actually propose? What's their solution?
So they've come up with this device, basically a microwave optical photon converter. You can think of it as a kind of universal translator, but for the quantum world.
A universal translator. I
Right.
like that.
And what's really amazing are its capabilities. First off, it converts up to, get this, 95% of the signal.
95. That's incredible efficiency.
It is, and with almost zero added noise. That's crucial.
Okay, 95% low noise.
Yeah.
What else?
Well, it fits entirely on a silicon chip.
Silicon, like the same stuff in my laptop.
Exactly the same base material, which, has huge implications for manufacturing later. But the real breakthrough part, it preserves those super delicate quantum connections. It keeps the entanglement intact between distant particles during the conversion.
That's the key, isn't it? Preserving the entanglement.
Absolutely. Oh, and it works both ways. Microwave to optical and optical back to microwave.
Okay, so it's efficient, it's silicon-based, it protects entanglement, and it's bidirectional.
Right. There's a great analogy from one of the study authors, Mohammed Khalifa. He said it's like finding a translator that gets nearly every word right, keeps the message intact, and adds no background chatter.
That really paints a picture. No lost meaning, no static.
Yeah, it nails the fidelity aspect. And UBC professor Joseph Selfie, he put it very bluntly, without that kind of converter, you'd just have expensive individual computers. With it, you get a true quantum network.
That really underscores the importance.
Right.
So it makes you wonder, how does it do that?
Yeah.
What's the mechanism inside this silicon chip that achieves this near-perfect entanglement-preserving translation where other attempts have, struggled?
Okay, so this is where it gets really clever, the stuff they detailed in NKJ quantum information. It involves creating these tiny engineered flaws in the silicon.
Flaws. That sounds counterintuitive for something needing such precision. You want flaws.
Well, engineered flaws, or more specifically magnetic defects, they're intentionally put there, very precisely. It's not like random imperfections.
Okay, so engineered magnetic defects. Then what?
So when you send in both the microwave signal and the optical signal, tuned just right, the electrons trapped in these tiny magnetic defects, they basically mediate the conversion. They allow one signal type to transform into the other.
Oh.
But here's the absolute genius of it. They do this without absorbing energy themselves.
Okay, so no energy absorption means less disturbance, less instability.
Exactly. That lack of energy absorption is what avoids the instability and, the signal destruction that has messed up other methods. The energy just passes through, converted, but not absorbed and re-emitted in some noisy way. It's elegant.
That is clever. And efficient, too, right? You mentioned low power.
Incredibly efficient. It runs on like millionths of a watt. Extremely low power.
Wow.
And yeah, the practical design they propose isn't just this special silicon. It actually incorporates superconducting components alongside it. So it's a smart mix of materials, science, and physics.
Right, bringing different strengths together.
Yeah.
It really highlights the ingenuity needed for practical quantum engineering these days.
It really does. And, while we're talking about the how, which is fascinating, it's important to zoom back out a bit. We need to remember this is still theoretical work at this stage.
Okay, right. So not something you can buy off the shelf yet.
Not yet. Dr. Salfi himself said, we're not getting a quantum internet tomorrow, but this clears a major roadblock. A major one.
And that roadblock is essentially sending quantum information reliably between, say, different cities, right? That's the big hurdle this tackles.
That's the one. But the really promising part of the silicon approach is the practical angle, because it's silicon.
It could potentially be made using existing chip manufacturing technology?
Exactly. The same kind of fabrication plants, the same infrastructure, maybe with some modifications, but it's not some completely exotic new manufacturing paradigm. That's huge.
Which means it could, theoretically, be integrated into today's communication networks much more easily than, I don't know, some giant fragile crystal setup.
Precisely. That integration potential is a massive advantage. It lowers the barrier to actually building this stuff out.
So if this clears a major roadblock, what kind of future possibilities does that open up? What could a true quantum network do?
Well, the implications are potentially transformative. Think about virtually unbreakable online security. Cryptography based on the laws of quantum physics itself.
Okay, unhackable communication. What else?
How about GPS that works perfectly indoors? Or GPS with just unbelievable accuracy, far beyond what we have now. Useful for navigation, autonomous systems.
Indoors GPS would be amazing.
And then there's the really big picture stuff. The ability to tackle problems that are just completely beyond the reach of even today's best supercomputers.
Like what kinds of problems?
Designing brand new medicines molecule by molecule, discovering new materials with specific properties, maybe predicting weather or climate change with dramatically improved accuracy, things that require simulating complex quantum systems themselves.
The scope is just vast, isn't it? It really changes the game for computation and communication.
It really does. So just to sort of wrap up what we've explored here, this UBC work gives us a silicon-based universal translator. It cracks that critical conversion problem between microwave and optical signals while crucially keeping quantum entanglement safe. And that pushes us much, much closer to the reality of a global quantum internet.
It really makes you stop and think. Almost every huge technological jump we rely on now, the internet, GPS, they started as theoretical ideas, often solving some communication puzzle that seemed impossible at the time.
Yeah, that's a great point.
And this silicon breakthrough, it feels like it's in that category. It's not just about, faster downloads or safer emails. It feels like it's fundamentally changing what information is, what it can do, and how far it can reach. So the final thought to maybe leave everyone with is, once this spooky action at a distance isn't so spooky anymore, once it's a seamless part of how we connect globally, what completely new, maybe even unimaginable applications are going to emerge from that? What's the next internet, the next GPS that we can't even picture yet?